All right, so I want to talk a little bit about solving systems of equations. First, talk about why we might want to solve systems of equations, and then think about some of the different ways that we solve them. So a question, we might ask is, how long would I have to invest my savings to want to choose a different account? So you might think, oh, maybe I'm starting with a certain amount of savings and one bank gives me a constant rate that's a little higher at the beginning, but another bank, the rates are increasing as time goes along. So I want to know, right, at what time period um, these two are going to intersect so that I know, am I going to be able to wait long enough for this account to be worth it, right? And so depending on how old you are and how long you're saving, it may impact which account you choose. And so finding that intersection can be important. Over what time interval will a ball I kick be above 20 feet in the air? I don't know why I'm missing the article there, but that's okay. So if you kick a ball up in the air, goes up, comes back down, let's say this is 20 feet right here, you could find the intersection of these 2 points and then basically decide how long, what time interval from here to here that the ball is going to be 20 feet in the air. If I start 3 meters behind, how much faster will I have to run in order to win the 100-meter dash? So let's say your friend starts here and you start 3 meters behind. Clearly, you're going to have to run faster. You have a steeper slope in order to reach the finish line at the same time. So if we found that, finish line value where they intersect, we could figure out maybe how much faster you need to go. So lots of reasons to use systems of equations. And while you may not use this every day, I actually used a system of equations to think about, a projected winner for the 2020 election just a couple days ago, and thinking about, okay, if so-and-so is winning by, this margin, if we continue to count votes, are they liable to, get ahead in a certain state? And so I actually used a system to make a prediction. I'm not sure if that's wise because, people do crazy things, but it was interesting for me to look at it. So let's talk about different ways to solving. And there are 4 I'd like to talk about. And so we'll look at the same system of equations and we will solve it 4 different ways. So first of all, I want to just point out that a system of equations has at least, 2 equations. And so for the ones we're going to be doing, it's going to be primarily 2, although it is possible to solve systems of equations with many more equations and many more variables. But we're just starting with 2 equations and 2 variables at this point. So the first method you might use is just numerical guess and check. And I actually think that we probably don't use numerical guess and check as much as maybe we should. But I will say some things about this. And one thing that I'm going to say about it is that it is often inefficient. Okay. However, it can give us a good sense of maybe some idea of what might work. I also think just like using numbers like this can be helpful just to get a sense for writing equations. So a lot of times if I'm given a word problem, I want to write down some numbers and then go to the algebra. But since the algebra is already here, this is probably going to be inefficient. So I actually don't know what the solution to this is. And so I'm going to guess, but I have no idea. So let's see here. Let's get this and let's just say, let's guess that the point is, I don't know, let's try one here. Well, if x was say -1, that would make this -6 up here, right? And then y could be say 1. Okay, so if I plug that into this one, I would get -6 minus 3, which is -9. So it definitely works for that equation. Now, if I plug it into the other one, I'll get -2 plus 2, which does not equal -6. So that definitely doesn't work. I'm wondering if maybe I could make x a little more negative. I'm really not sure. It's really not going to be easy. Maybe I could try, say, -2. How about -2 and 1? No, that's not going to work. Because these maybe both need to be negative, I think. What about -2 and -1? If I did -2 and -1, yeah, I think that might work. Because if I plug in -2, 6 times -2 minus 3 times -1 is equal to -9. That's a question mark. I'm wondering if that's true. I'd get -12 plus 3 equals -9. Yes, -9 equals -9. So it works for that equation. And on the other one, I would get 2 times -2 plus 2 times -1 equals -6, question mark, does it? -4 minus 2 equals -6. Yes, -6 equals -6. Okay, so it looks like this is actually the solution. Now, I sort of, thought about that a little bit and figured it out, but you can see that the guess and check is a little bit difficult to figure out. But it does look like 2, -1 works, and you'll notice that it has to work for the first equation and it has to work for the second equation, right? Otherwise, it wouldn't solve the system of equations. So that's something I would do a lot of, but you can try to give yourself, a sense for what's going on and also to practice your sort of numerical fluency. All right, method number 2 is graphing. Now, graphing is great for estimation, but if done by hand, it can really only give you an estimate. It's hard to make precise. Okay, so I think graphing is just a little bit hard to do by hand, but I really, really encourage you to always use graphing when you're solving equations and systems of equations to give yourself a sense for what is probably going on. And if you have a graphing calculator or Desmos, this can be a great method. So if you were going to do this by hand, what you would need to do is put them in slope-intercept form because these are lines. So let's go ahead and put them in slope-intercept form by solving for y. So the first equation, second equation. So first equation, we'll say that -3y is equal to -6x minus 9. I just subtracted 6x from both sides. Now I'm going to divide by -3 and get y equals 2x, right? Because -6 divided by -3 is 2, plus 3, because -9 divided by -3 is 3. Okay, so that's the first equation right there. Now the second equation, I start with 2y equals -2x minus 6. So y is equal to -x minus 3 when I divide everything by 2. And now I'm in slope-intercept form. So let's go ahead and graph these two lines and see if we can confirm our answer, which we got back here, which was -2, -1. So this line has a y-intercept of 1, 2, 3 right there, and a slope of 2. So over 1 and up 2, over 1 and up 2, down 2 and to the left 1, down 2 and to the left 1. So it should look something like this. So that's 2x plus 3. And our other equation, y equals -x minus 3. 1, 2, 3, -3. And then up 1 over 1. Up 1 over 1. Up 1 over 1. So even now my graphs are a little bit off, but it does look like that they intersect at the point -2, -1 as expected. Okay, so that intersection point is the solution. And going back here, we know that if we were to plug it in, it makes both the equations true. So the thing about this is if I were just to graph this, I don't know if I would get exactly on there, but at least I would know, hey, I think it's in quadrant 3. And so it would give me a sense, at least, for where my answer should be. You can also use Desmos. I won't do that, but of course, Desmos is going to be more accurate. Your calculator is going to be more accurate. So that's a great technique as well. Okay, finally, we move on to method 3, and then there's one more after this. And method 3 is substitution. And you've probably done this before, but how this works is solve for one variable in one equation. Then plug that solution into the other equation and solve. Then plug that solution back in to the original, or either. Okay, so it's a little bit hard to describe in words, but basically what we're going to do, right, is, whoopsie daisy. Basically what we're going to do is solve one of these equations for x or y, then plug that into the other. So one thing I like to do is to keep my equations separate when I am doing substitution. So I'm actually going to draw a line here, and I'm going to write one equation, which is 6x minus 3y equals -9 on this side, and 2x plus 2y equals -6 on this side. Now, it doesn't really matter which variable I solve for in which equation, but pick the easy one. I tend to like 2's a little bit better than 3's and 6's and negatives, so I'm going to solve for y. And to do that, I'm going to subtract 2x and get 2y equals -2x minus 6. And then I'm going to divide by 2, divide everything by 2, and get y equals -x minus 3. Okay, so now at this point, I have solved for one variable in one equation. Now I'm going to plug that in to the other equation. This is equal to y. So I'm going to plug this in for y over here, right? Because that's equal to y. Y is equal to -x minus 3. I can't plug it into the original equation. Then I'll just get something that's true, like 2 equals 2. So when I plug that in over here, I am going to end up with 6x minus 3 times, parentheses are your friend here, -x minus 3, and that's equal to -9. So you see how I just replaced y with -x minus 3. Now I need to solve. And the nice thing that you'll notice is that I have gotten rid of a variable because I substituted this in for y. So now I've got 6x plus 3x plus 9 because I'm distributing -3 to -x, and -3 to -3 is equal to -9. I'll add these two to get 9x. I'll subtract 9 from both sides, so 9x equals -18. Divide by 9, divide by 9, and I have x equals -2, which, going back here, is what I expected. It's what I expected. Going back to my guess and check, numerical guess and check, my graph, and now substitution. Now I need to take that and plug it into either equation, but I'll just plug it in here because that's easy to get my y value. So my y value now, I'm going to have y is equal to -2 minus 3, which is +2 minus 3, which is -1. So my solution is -2, -1. That is the point that makes both of these equations true. So that's substitution, right? Solve for one variable in one equation, plug that solution into the other equation and solve, and then plug that back into the original or either equation. It really wouldn't matter. You just need to plug that last one back into one of the equations. All right, our final method is linear combination, aka elimination. And this one is definitely maybe the one that's hardest to grasp, but it's also one of the most efficient, and it can be really, really elegant. And so what this basically uses is this idea. The idea that if you have 2 equals 2, which is true, and you have 3 equals 3, which is true, if you add these two equations, you will get 5 equals 5, which is still true. If you have 2x equals 3, and you also have 5x, no, not 5x, let's erase that. You know, you have, let's say, 10x is equal to 15. If you add these two and get 12x is equal to 18, that's still true. Okay, so basically what we're saying is if you have true equations, you can add them together and they will still create a true equation. Now, if we added these together right now, plus, 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 we would get a true equation. We would get 8x minus y is equal to -15. But this is not helpful. And it's not helpful because it's true, but it's not helpful. It's not helpful because what we want to do is eliminate a variable. That's why it's called elimination or linear combination. So we have to manipulate our equations a little bit to make sure that we can basically eliminate a variable. So it's true if we just added them straight off the bat, but it's not helpful in this case because we didn't eliminate a variable. Okay, so I think I kind of destroyed part of my thing there. But this said 6x minus 3y, and this is 2x plus 2y equals -6. So what we need is we need the following. We need the coefficients of either x or y to be opposites in the two equations. I like to have opposites and then add the two equations. You may like to have the same number and then subtract, but I don't really like subtraction because it just confuses me. Well, it doesn't really confuse me. I just think that it's easier to make mistakes with subtraction. So we need the coefficients of either x or y to be opposites in the two equations. So what do I mean by that? I mean that if this equation is going to be 6x, I want this to be -6x. If this is going to be 3y, I would want this to be -3. So you want those to be opposites so that when you add the two equations, you can basically eliminate a variable. So there are a few different things we could do. I'll tell you what I think is the best way. Best way, I think, is that we could just multiply this bottom equation by -3. And if we multiply it by -3, which is fine, remember, if you have 2 = 2 and you multiply both sides by -3, then you have -6 equals -6. That's still true, right? You can multiply both sides of an equation by any number if you want to, so long as it's not 0. So I could multiply this by -3, and then the coefficient of x would be -6x. Another option would be to multiply this one by +3 and the top one by 2, because then I would make my coefficient of y -6 and my coefficient of y down here +6. But that's more steps, so I'd prefer not to do that. I prefer to do fewer steps. I'm a mathematician. I'm a lazy mathematician. So let us multiply by -3. Okay, so we're going to rewrite the first equation exactly as is. 6x minus 3y equals -9. Now we're going to multiply the bottom equation, and we're going to write -6x minus 6y is equal to 18. So I multiplied that by -3, that by -3, and that by -3 to make sure that my equation is still balanced. Finally, I'm going to add these two together. Now 6x plus -6x is 0x. -3y minus 6y is -9y. And -9 plus 18 is 9. So I end up with this is 0, gone, by. So I end up with the equation 9y equals 9, -9y equals 9, rather. And so y would equal -1, which is what I expect. Now I can simply take this value and plug it back into an equation to find x. So 6x minus 3 times -1 is equal to -9. That means 6x plus 3 equals -9. 6x equals -12. And x equals -2. So again, I have my point -2, -1. Okay, so we will practice linear combination and elimination more. But what you want to know is that you need the two coefficients. You need the coefficients of either both the x's or both the y's to be opposites in the two equations. Then you can add the two equations and eliminate that variable, and then you're well on your way. So once you know how to do it, actually very efficient and beautiful. Okay, in summary, let's just go back through our slides very quickly. Lots of reasons to solve systems of equations beyond the obvious beauty and poetry of mathematics. So you can just guess, try and find the numbers just by guessing and plugging things in. A little inefficient, but gives you a good sense of what's going on. You could graph, always a good idea to think about, how things are and estimate where solutions are, but a little imprecise if you're not really good at graphing, or if you have any sort of weird numbers or you don't have a calculator. You could use substitution, which is a great method. Solve for one variable, plug that into the other equation and solve, and then plug in again. Or you could use linear combination, aka elimination, which I think is a great method, but it does require a little bit more thought to make sure that things are prepared. Okay, sometimes one method is better than the other. And so you want to be flexible in choosing which method you use. Okay, hope that was helpful, and I'll see you soon.